Don't worry, there's no antimatter here. All right, thanks, David. So why do we need better rockets? And what's wrong with the rockets we have now? That's an interesting question. In order to answer that, I need to talk first a little bit about rocket science. So I know David asked me not to put too many equations in here, but I am a physicist, so there's going to be at least one equation. I think you guys can handle it. It's basically the rocket equation. So it explains how fast can a rocket go. It's pretty simple, actually. So it only depends on three things. First part, VE, how fast can you exhaust things out of the back end of your rocket? So that's the exhaust velocity. So MI and MF, the initial mass of your rocket when it's full of fuel, and MF when it's, when it's full, and the final mass when it's empty. So it really only depends on three things in terms of how fast you can go. So in 1926, Robert Goddard, you can see him there with his rocket, developed liquid propulsion. And so he really developed the ability to maximize that exhaust velocity. And we still use the same fuel, basically. So what have we done between 1926 and 1974? We've really focused on those other two factors, the initial mass and the final mass. So that by 1974, you had rockets like the Titan III up there on the right that was 90% fuel. And these days, it's up towards 95%. So that's really what we've been focusing on in terms of advancing rocket propulsion. And I show the picture on the right because that Titan III rocket actually carried the Voyager 1. And Voyager 1 is the fastest man-made object we've ever created. It goes 14 kilometers every second, which seems pretty fast. And it left the solar system actually a couple of years ago. But the problem is that's actually really slow, 14 kilometers a second. And the reason is that things in space are incredibly far apart. To put that in perspective, if you want to go to the Earth to Mars, 50 million kilometers, it'll take several months, even if you're going at 14 kilometers a second. If you want to go to Pluto, and NASA recently did this, they sent the New Horizons. It took 10 years to get there, took $1 billion, but we did get some really nice photos. And the really difficult thing is if you want to go to Alpha Centauri, our closest star system, it's 38 million kilometers away, which it's not really a meaningful number, but 30,000 years to get there if you're going 14 kilometers a second. That's really far. So it's clear that we need much better rockets. We need a much better way to get out of here, especially if the AI takes over, as we've seen. So before I get into the propulsion concepts, I got to talk a little bit about antimatter origins. Where does antimatter come from? Of course, in the early 1900s, we had quantum mechanics. We had Max Planck telling us about uncertainty and wave-particle duality. You add to that special relativity. So the maximum speed limit is the fact that time and mass are dilated the faster you go. And you put those two together. And Paul Dirac was actually over here at Westminster. I went to see him the other day. He came up with the combination of quantum mechanics and special relativity, called it relativistic quantum mechanics. He came up with a set of equations, and he solved that for the energy state of a free particle, and he got positive solutions and negative solutions in energy. And most people, when you're solving a math problem, you see a sign error, and you just disregard the negative one. Oh, let's take the positive one, right? But Paul Dirac actually said, no, wait a minute, maybe that's indicating something. Maybe the math is telling me that there's actually a new class of particles. So he came up with what he termed mirror matter, so the mirror of normal matter. And everybody thought he was crazy for a little while. But 4 years later, Carl Anderson at Caltech says he's looking at cosmic rays in bubble chambers. So he sees this weirdly shaped particle. It's got the curvature of an electron, the mass of an electron, but it's curving the wrong way. It's going left when it should go right. And so he says, well, maybe this is what Paul Dirac was talking about. He called it the anti-electron. And that's what later was called positrons, which is what I work with. So What have positrons been up to since 1932? Well, you can see a picture here of a cyclotron. So a cyclotron is a factory for antimatter. And this isn't in a physics lab. This is in the basement of a hospital. So what is it doing there? So it turns out if you take a cyclotron, you can create a radioisotope that emits positrons. You have a patient that you think has a tumor. You have them swallow the antimatter. So you might know someone who actually has swallowed antimatter. And then you get these nice images of tumors. And you saw in the last talk, actually, some pictures of PET scans. So PET scan is actually positron emission tomography. So that's really what the main use of positrons has been for the last 50 years. My interest in positrons is a bit different. Annihilation. Annihilation is a property of antimatter that's very unique. You have a block of antimatter, you hit it next to matter, and it annihilates into pure energy. And that's sort of the purest form of mass to energy conversion that you can get. And to put that in perspective, you see a penny on the left, you got about 20 grains of salt. Now if that were anti-salt, and you smash it into salt, you get about 2 times 10 to the 13 joules. That doesn't really mean much to you, but it's about the same amount of energy as all 4 million pounds on the space shuttle. 4 million pounds of rocket fuel, that is. And also, it turns out that that's actually the same amount of energy that London uses in 24 hours. So incredibly energy-dense material, so that's what interested me, and what I wanted to utilize in some propulsion aspect. Now, the Positron Dynamics story started several years ago. I was finishing up my PhD in physics, and I was also working on a separate project called the Google Lunar X Prize. It's a privately funded project to send something to the moon and bring video back. So I was working with a group of engineers on the propulsion aspect. Here we are in the Mojave Desert testing a rocket, and there was actually another positron physicist there, which is kind of a coincidence. There's only about 50 of us out there in the world. So we were driving back to the airport. We started thinking about what could we do if we had a lot more positrons than we currently can produce. And it turns out you can do some pretty amazing things. And the real key challenge was that we couldn't cool them down efficiently. So current state of the art in positron cooling, you throw away 999 out of 1,000 positrons. So it's very inefficient, and you don't get very many cool positrons. And having cold positrons is very important because you can't control them realistically with magnetic fields and electric fields without them being very cold. So we focused on, we threw around some ideas in terms of how can we cool down positrons more efficiently. We wrote on napkins, and we basically developed a patent that was a way to cool down positrons efficiently using crossed magnetic and electric fields as well as combination with semiconductor material. So we got some funding to try this out from the Thiel Foundation in the Bay Area. And it turns out that, as you can see a picture on the left, that's us with our equipment back in 2012 in an office building. You shouldn't do nuclear physics in an office building. So we got kicked out immediately. We found a warehouse, which is nice, a little more appropriate. So back in last year, we were able to put the system together, and we were able to demonstrate that we can actually do efficient positron moderation, the process of cooling down positrons, so that in this year, we actually moved into a nuclear fallout shelter. Turns out it's much better for nuclear physics. And we started focusing on ideas to try and produce a rocket based on the positrons, as well as we filed some patents in that area as well. So I'm going to talk a little bit about our concept. I won't get too detailed in the physics, but it's based on a radioisotope. So we don't need a nuclear reactor. We don't need a huge linear accelerator. We just buy this radioisotope from actually a company in South Africa. It's sodium-22. It comes in liquid form, so we deposit it on a thin film. We run it through our moderator, and this year we've developed sort of a more mass reproducible semiconductor version of that hand-built thing that we use to prove the concept. We run it into a thin film, And that thin film has a deuterium isotope, or a hydrogen isotope, deuterium, that is the fusion fuel. So the annihilation process that I talked about earlier really catalyzes a fusion reaction, and then we get the fusion products to produce thrust. So this next year, what we're trying to do is integrate that into a CubeSat, which is a small satellite platform, in order to demonstrate that in orbit. So to put that in perspective, last time we tried to do something really innovative in propulsion in space, it was the NERVA program. You may be aware that we tried to launch a large nuclear reactor into space in the 50s. The American public didn't want us to do that, so it was canceled. But what we want to do is launch a CubeSat. So a CubeSat's this size. This is actually 10 by 10 by 10 centimeters. And we can actually package our propulsion system in a very small form factor, so shoebox-sized satellite, and prove that we can actually do this in space. So that's all well and good, but how do we make money off that? Well, it turns out that there's probably 5 to 10 companies that want to launch constellations of satellites, so up to 1,000 satellites each. And the reason they want to do this, for example, Google Skybox wants to create sort of a live Google Maps of the Earth. Samsung wants to launch 5,000 satellites in order to create global broadband internet, and the same thing with OneWeb, SpaceX. So all these companies want to get up into low Earth orbit. The problem is they don't have a good solution for propulsion. So their satellites aren't going to last very long in low Earth orbit. But if you put our positron propulsion system on it, you can actually last up to 7 years. You can actually orbit at a much lower altitude, which gives you much better image resolution and bandwidth. So that's where a lot of the value is in low Earth orbit for our systems. A little bit further down the road, asteroid mining. You probably haven't heard of it, but it's going to happen. So you take a 100-foot wide platinum-rich asteroid. It's worth about $10 billion here on Earth. So right now we don't have the technology to go and get them and bring them back. Chemical and electric propulsion is not going to be able to do that. So we need something like an antimatter-based propulsion system just to be able to do that. So early 1900s, Wright brothers, a lot of people thought that human flight wasn't going to be possible. I mean, they showed that it was possible. And then 60 years later, we had the SR-71 going 1,000 times faster. So what does that mean if we could go 1,000 times faster than the current state of the art? Voyager 1 at 14 kilometers per second is the fastest thing right now. If we could go 1,000 times faster, we'd be going around the world in 3 seconds. Incredibly fast. And that means we can get to Mars in weeks. We can get to Pluto in a matter of months. And really, the most exciting thing for me is we can actually become interstellar species. We can actually send something to our closest neighbor, Alpha Centauri, in a matter of 40 years, so in our lifetimes. So that's what excites me about this technology, and thanks for having me.
Just want to ask, what happens when an antimatter rocket scientist goes into the office in the morning? You've picked up your Starbucks coffee on the way, you log on your computer. What happens next?
Well, it's not too glamorous. A lot of our stuff is vacuum science. So we have to create ultra-high vacuums systems, so we have to simulate space. We can't do any of this on Earth because there's just too many particles in the air. So a lot of the equipment that we have to upkeep and we have to run is all vacuum-based systems. So that's kind of the non-glamorous side of things. Yeah.
And let's have a look at your little friend again.
Oh no, there's no antimatter in here. Don't worry. So you can get close to it. This is actually just demonstrating a sort of a mock-up of our propulsion system and the size of it. So,
what's the current cost of sending CubeSats up?
So it costs about $20,000 per kilogram to send something up there. So CubeSats actually are a modular system, so you can stack them together based on what kind of functionality you need. So our initial demonstration, we're shooting for a 6U CubeSat, which is 6 of these things put together.
And presumably the Moore's Law price reduction is hitting in as well.
Yeah, so as the technology for launching things into space isn't changing fundamentally. It's still chemical-based propulsion, liquid oxygen, liquid hydrogen. So that cost is going to be relatively unchanged in the near future.
So last quick question. How is your work going to affect the lives of people in the room maybe over the next 5 to 10 years?
Well, as I said, a lot of the applications in low Earth orbit are going to be our initial market. So in terms of all the data from agricultural data is going to be huge, and things like Google Maps tracking like that. You know, that's not to mention any of the military applications as well. So
I don't think we want those.
yeah, we'll talk about that.
Thanks for joining us, Ryan.
Thanks, David.